Good morning, everyone. My name is Anna Farquhar and I am a research scientist at Aeroqual in Auckland, New Zealand. And today I want to talk to you about some of the research I've been doing on electrochemical gas sensors, and in particular focus on how these gas sensors respond to changes in the environment or in the atmosphere and how that might impact their use in ambient air monitoring. So to begin with, I just want to take you through the basics of electrochemical gas sensor measurements. And in particular, I'm going to focus on gas sensors for oxidizing gases. So those are NO2 and ozone. And in these oxidizing gas sensors, we measure the combination of NO2 and ozone in the atmosphere. How these sensors work is the target gas will diffuse through this membrane and come into contact with the working electrode. When the gases contact that working electrode, they will be reduced, and that will generate a negative current. And this negative current is directly proportional to the concentration of NO2 and ozone combined in the atmosphere. So at Aeroqual, we regularly use these gas sensors to detect NO2 and ozone in ambient air, and we're able to get fairly reliable measurements down to ppb levels. So I want to show you some results that we have generated from a long-term study using these electrochemical gas sensors that has been running since August 2019 in Denver, Colorado. And I want to first go through how the gas sensor responds to target gas, and then look into how the sensor response is impacted by the dew point. Now I'm going to focus on dew point because this is a measure of the absolute humidity, or the amount of water vapor that is present in the atmosphere. So in this study that we did in conjunction with the US EPA and the Colorado Department of Public Health and the Environment, we set up one of our Aeroqual AQY units that has an electrochemical gas sensor in it, and we co-located it with a reference station. And then we were able to record the data from this electrochemical gas sensor from August 2019 until the present day. And so down the bottom here, I've got some of this data. The red shows the electrochemical gas sensor output, and the black is the reference station output, and the blue line is the dew point of the surrounding atmosphere. So you can see in August, the reference and the electrochemical gas sensor data agree very well with one another. However, as the year progresses, we start to see this discrepancy between the reference station and the electrochemical gas sensor data. And this seems to coincide with this decrease in dew point that we see in these colder winter months. But at the start of 2020, when we're getting into April and May, and this dew point is coming back up, so the absolute humidity of the environment is increasing, we start to see that the reference and the electrochemical gas sensor data agree with each other once again. So the overall trend that we're seeing is when we get this decrease in dew point below around 0 degrees, we see this offset between the reference and the electrochemical gas sensor data. However, we are able to return to this good agreement when the dew point comes back up. So I now want to just focus in on a couple of months throughout this year to really see if we can understand this relationship we're seeing. So you can see in August, the red, which is the electrochemical sensor output, and the black, which is the reference station output, agreed fairly well with one another, especially in terms of the baseline concentration. However, in January, when the dew point has dropped very low, so we're in a dry environment, you can see that the electrochemical gas sensor data is significantly offset from the reference station data, and so we're reading overall a lower concentration of our target gases. Then in March, things get quite interesting. In March, the temperature remains fairly constant throughout the month, but the dew point starts off quite low, and as the month progresses, you see the dew point is slowly increasing. And you can see that as that dew point slowly increases, the electrochemical gas sensor output and the reference station output slowly start to agree with one another once again. So when we have this low dew point at the start of the month, we have that offset between the reference station and the electrochemical gas sensor data. But when the dew point has come back up to more average values, we're seeing good agreement between our reference station and our AQI data. So that's the results from a steady state long-term perspective. We see this offset in the baseline concentration as a result of changing dew point. But the next question I had was, well, what happens if you look at shorter duration data? So here I have 1 minute data from both Auckland, New Zealand, and the station that we looked at in our Denver, Colorado study, to see what happens when you get very rapid changes in dew point rather than these slow sort of monthly changes. So in the Auckland data, you can see the black line is the reference station and the red is the electrochemical gas sensor output. And you can see that when we have a gas peak in the reference data, we also see that in the electrochemical gas sensor data. However, throughout the day, we see these concentration spikes that are not seen in the reference station data. And these spikes appear to coincide with rapid changes in the dew point. And if you plot the change in dew point versus the change in concentration, you can see that we have a positive correlation between a dew point change and a concentration spike. And we see the same thing over here with our Denver study. So we're seeing this increase in these concentration fluctuations throughout the day when the dew point is changing rapidly. And so we have two effects. We have our steady state behaviour that causes a shift in the baseline concentration, and we have this high-speed data that gives us these concentration fluctuations that are caused by sudden changes in the dew point. So I wanted to simulate some of these results in the lab to see if first we could hypothesize why this is occurring, and secondly come up with solutions to mitigate these effects. So the way that I studied these effects was by using this solenoid to switch between humid air and dry air. So in this case, the dry air was just the humidity of the lab, and the humid air had been humidified by passing it through naphthalene and water. And so then we can put that air across our gas sensor and record the gas sensor output, and then measure the temperature and the humidity of that gas stream. Now I did all of these experiments in this insulated box so that the temperature was constant, and I only ever used zero air. So in the later experiments that I will show you, there is no target gas around. So every concentration spike we see is associated with this change in humidity or dew point. And so this is what that looks like. Here on the left, I did sort of a slower study. So you can see if you go from dry to humid to dry to humid, we get these concentration spikes, and then we decay to this new steady state value. And these concentration spikes appear to correlate with dew point. So the magnitude of the concentration spike depends on the magnitude of this dew point switch. And then we can see that change in the baseline offset at different humidity levels. And then here on the right, I simulated what we see in the real world. So down here is the dew point changes, and they're changing of about 1 to 2 degrees over 1 to 2 minutes, which is what we see during the day here in New Zealand. And you can see that the concentration output matches very well with that dew point output. And so we're getting this high noise that looks like these massive concentration spikes caused simply because the dew point is fluctuating rapidly during the day. And the magnitude of these concentration spikes due to dew point is similar to the magnitude of the concentration levels that we see of our target gases in the atmosphere. So these dew point fluctuations really complicate the signal that we're getting from our target gases. So why are we seeing these changes in concentration reading when we change the dew point? So at the moment, our hypothesis surrounds the idea that changing the atmospheric humidity will change the concentration of the acid in our sensor. So in an electrochemical sensor, we have our electrodes, and these are all submerged in sulfuric acid. And this sulfuric acid is in equilibrium with the atmosphere. So if we change the atmospheric water vapor content, we will change the concentration of the acid, and that will do a number of things, which I've listed here, but two very important ones are it will change the rate of the oxygen reduction reaction, which is what causes the baseline current, and so if we change the rate of that reaction, we may offset our baseline concentration. And it also changes the capacitance of this working electrode. And if we change the capacitance of the working electrode, it will need to be recharged, and that will cause a current spike, which will manifest as those concentration spikes we saw in our earlier readings. So how do we overcome this? Well, for the steady state effects, it's quite straightforward. We can simply apply a mathematical algorithm to bring that baseline back up. However, for the transient effects, it's a bit more tricky to use maths. And so we have found that by placing a sample conditioning material in front of the sensor, we are able to block that transient behaviour. And so the sensor never experiences this dew point change. And so we get no fluctuations in our baseline concentration. So to wrap all that up, we can use these electrochemical gas sensors to measure target gas concentrations in ambient air, but they are very sensitive both to steady state and rapid changes in the dew point. And so we really need to consider that when we're using these sensors in an ambient air monitoring application. So thank you for listening, and I'd be happy to take any questions.